Recently, I watched an amazing video by the YouTube channel Veritasium about a riddle involving 100 prisoners. What makes this riddle so amazing is that the answer is counterintuitive, yet the math proves it to be true. It's an amazing video. I would recommend checking it out if you haven't already. But after watching it, as a data scientist, all I could think of is, can I code up a simulation to this problem? I've found that as a data scientist, often coding up problems like this help you to gain a much more intuitive understanding of exactly what's going on. So after a few days of struggling to write the code, I finally got a working solution, and I was able to recreate a few of the graphs that Veritasium showed in his video. So in this video, I'm going to show you how I coded this up in Python, and I'm even going to link to you the notebook in the description. So if you want to go into it and check out the code yourself, feel free. Okay, so let's jump into the code. Okay, so here I am in a Jupyter Lab session, and like I said, I'm also going to share the notebook here as a Kaggle notebook so you can look at the code later. But we're going to be simulating the 100 prisoner riddle. There's 100 prisoners. There's 100 drawers or boxes with random numbers in them between 1 and 100. They each go into the room one at a time and pick 50 boxes. They need to find their own number, and they can't work together. They can only strategize beforehand as to what they're going to do before they go into the room one by one. To succeed, they all 100 need to find their own number in the boxes. If one prisoner does it incorrectly, they all lose. So we are going to code this up in Python, and we're going to start with some imports. We're going to import pandas, numpy, tqdm, trange, because we're going to be doing some loops in the simulation, and we want to see a progress bar as we loop through. We're also going to use network X to show a graph representation that we'll see is important in the solution that works. And then some plotting libraries. This extension LabBlack will allow us to auto format our code as we run each cell. We want to first start out with the boxes that we have in this riddle that have randomly been given a slip of paper with the numbers between 1 and 100. So let's represent these boxes as a Python dictionary, where the key is going to be the number of the box, and the value in that dictionary will be the number of the paper slip within the box. In order to populate this box's dictionary, we're going to loop through all the prisoner numbers. So let's make a list of prisoner numbers, X for X in the range of 0 to 100. Now in Python, we like to start at the number 0 instead of 1. So our prisoner numbers, if we look at them, are actually going to be from 0 to 99 here. Now, the nice thing about numpy is numpy comes with a built-in random package. With random, you can do a handful of things, but we're going to actually use random shuffle to shuffle this prisoner numbers list. This, if we could see, every time we run it, actually runs in place and updates this prisoner numbers. So let's run it a few times. You can see that it's just shuffling randomly this list up into a different order. And now we're going to take this shuffled random prisoners, and we're going to populate the boxes by doing let's find the index location and the prisoner number in enumerate. Enumerate just allows us to loop over this prisoner numbers list and have an index value, that's this I. We're going to take all the boxes and populate in each box. So this number is going from 0 to 99. It's populating with the shuffled prisoner numbers. So if we run that, we can now see that our boxes is a dictionary with values 0 to 99 and the random prisoner slips in each of the fields. So we want to make this into a function, and we're going to call it shuffle boxes. So every time we run this, we can return this boxes, and we can do something like this, boxes equals shuffle boxes. And every time we run this, we will get a different shuffled box with randomly distributed paper slips for each prisoner. Let's also make some constants. Prisoners is just going to be numbers between 0 and 99, and then the box numbers. Okay, so let's start first with the random choice strategy. Now the random choice strategy is if the prisoners did not have any strategy going into this, they would each choose just 50 random boxes when they go in, and they'd either find their own number or not. So we're going to use numpy's random again, but instead this time we're going to use choice to choose out of our box numbers. So we're going to choose out of our box numbers size of 50, and then this is really important. We're going to put replace equals false. So that means that we're going to choose 50 numbers out of the box numbers, and we can't repeat choosing the same number twice because the prisoners will choose 50 unique boxes. All right, so if we run this, each time we see that it's just choosing 50 random numbers out of the 100, and we'll call this the prisoner choices. But now we want to see if the prisoner number is actually in these prisoner choices. So let's assume our prisoner number equals 1, and then we're gonna say if prisoner number is in prisoner choices, print yes. And we're gonna actually make this into a function where it will return true if this is correct, and otherwise it will return false. So we're gonna shift this over, and we're gonna call this random strategy. It'll take in the prisoner number and the boxes. So I'm just gonna give it a doc string here, which I've already written. And we can test this out by doing random strategy, prisoner number, let's say the prisoner number 50 and the boxes. We're gonna run this a bunch of times. You can see sometimes it's true and sometimes it's false. It should be about 50-50 odds of them being true or false. Now remember, we have 100 prisoners that are going through and trying this strategy. So we're gonna make a function called try strategy, and it's gonna take in the boxes and the strategy function that we've created before. This is gonna show out of the 100 prisoners, how many of the 100 got their correct number, how many actually found their number and succeeded. Remember, in order for them all to succeed, they all need to find their own number. So prisoner, we're gonna loop through each prisoner in the prisoners list, and we're gonna see if it's correct by running our strategy. And we're gonna give the strategy the prisoner number and the boxes. And then if it's correct, we'll take the number correct and we'll increment it. And then we'll return finally the number correct. And of course this needs to be bumped out. So now I can see by running this function, we see the result of how many of the prisoners actually got their own number. And just running it a few times, we can see it's never hit 100, so they never succeeded. But we're actually gonna run this simulation a bunch of times to see what the distribution of these results are. So we're gonna do this by looping a certain number of times, and we're gonna store our results in a dictionary called results. And we're gonna say for simulation in T range, and we're gonna do 5,000 simulations. We could also just say number of simulations equals 5,000. That's a little cleaner. And remember, each time we want to create new boxes, so we'll run our shuffle boxes, and then we'll find the number correct by trying this strategy. We're gonna give the strategy the boxes, and the strategy is our random strategy, and we'll store this in our results dictionary. So this will take a little while to run because we're running the simulation 5,000 times. And we could make this more just to get a better idea of the distribution, but 5,000 seems good enough for now. And what we have here is a dictionary where the key is each simulation, and then the result is the number of prisoners who actually succeeded. But I want this as a pandas data frame because that's a little bit easier to work with. And so we'll make a pandas data frame from this dictionary. We need to do a few things like orienting it by index, and we'll call the columns n correct for the number of prisoners that were correct. And let's call this data frame results random. Now, a few things we can do with results random. We can look at the number correct and the mean value. We can also look at the standard deviation. So we can see the average value is 50 and the standard deviation is about 4.9. But to better visualize this, let's actually make a bar plot similar to what was seen in the video about this riddle. This part is mainly just for plotting's sake, so don't get too hung up if it's not making a ton of sense right now. And I'm gonna make a plot out of this, and it shows us this distribution of number of successful random choices. And you can see the distribution here is centered around 50. That's what we would expect, and it's a normal distribution because they're just randomly choosing those 50 boxes each time. But almost never do they, actually never in this simulation, do they get all 100 correct. Now we know through the math that if there's a 0.5 chance of them being successful, and we need all 100 of the prisoners to be correct, the odds of them all being correct is 0.5 raised to the power of 100. And this is a very small number. Just to show this visually too, this number actually looks like this if you write out all the zeros. So it's almost impossible for all 100 of them to get their number correctly. But we're gonna look at the awesome solution and strategy that they can go into it and up these chances to almost 31% chance of success. And that's the loop strategy. So this strategy is so simple, yet effective, and all it is that the prisoners agree that when they enter the room, they will first start with a box that there is their own number. And then they'll go on from there and select the next box based on whichever paper is inside of the box they chose before, and so on until they get to 50 boxes, and hopefully they will find their own number. So in order to code this up, we have our prisoner number. Let's start with an example of prisoner number 1. So what is prisoner number 1 gonna do? They're gonna take the boxes and they're gonna first look at their own box number, which is prisoner number. So happens that takes them to box number 50, so then they're gonna look in box number 50. Now in order to code this up, let's just say the next box is a value and it's going to start as the prisoner number. And then we're going to say for X in range 50. So they're going to go through 50 different boxes and they're going to look up this next box value. Now, if that happens to be their prisoner number, their own number, they're going to have found it. Let's do a print statement. If not, the next box will then become the result of this. Of course, this is an if statement. All right, so in this example, they found it. They went through the loop and they went through it and they found their own number. Let's make this into a function though. And we're gonna call this loop strategy. So this is gonna take in the prisoner number and the boxes. And then instead of saying found it, it's gonna return true. Actually, this needs to be like this so that they run it 50 times. They'll return false if they don't find their own number. So this is correct. And I'm gonna actually add this doc string that I wrote up before to summarize this strategy. And now let's do this strategy again, exactly like we did before, 5,000 times and see what the results look like. Oh, I did mess this up. So the next box is gonna start as the prisoner number. Okay, so now we're gonna run this strategy of looping through, and we're gonna run the simulation 5,000 times again and see what the results look like. We're gonna store these results in this results loop dictionary. We can see now that the average value is still close to 50 that get correct, but the standard deviation is much larger than before. It's actually 35. So let's plot this out using the same code that we did before, because that's really gonna help us see what the results look like. So now we see here the difference between the distribution in our simulation. A lot of the times the prisoners will actually get less than 50 correct, but then there's a big gap and they actually 31% of the time get all 100 of the prisoners to have the correct result. And we can double check this by taking our results loop data frame, which we have here is the number, and we'll see when the number of correct equals 100. So this means they're successful. What's the average amount of time that occurs? So here it's 30.8 or about 31% in our simulation that the prisoners have succeeded. So that's interesting, but how exactly does this work? How, just using the simple strategy of choosing the next box based on the number in the previous box, do the prisoners make their odds of success so much higher? Well, the key is that each of the boxes are actually linked to each other when this strategy is taken. So you can think about the boxes now as a graph, where this network graph has a box pointing to the next box, and we're going to visualize this. And what actually happens is if the largest loop of boxes is less than 50, then the prisoner is guaranteed to find their own number on their loop. And they're guaranteed because they started on the box that is their own number. It sounds crazy, but we're gonna see visually how this works. And we're gonna visualize this using the Python package NetworkX. And we are just going to start from scratch and create a new set of boxes by running our shuffle boxes. Then we're gonna create a NetworkX die graph. So this is a directed graph where each box is pointing to the next one because of the note inside of its number. And then we're gonna add nodes from box numbers. Now we have this graph object, and we can draw this using NetworkX's draw. And we're gonna say with labels to make it easier to read. And let's go ahead and show that. So now we see in our graph, it's not much of anything yet. We have a circle that represents each of these boxes that they can choose from. We can use our dictionary that we created to create edges in this graph. So our edges are just gonna be X and Y for X, Y in our boxes items. If we look at this edges, you can see how it's just the link between these. And then we're gonna add the edges to this graph using the add edges from, and we're gonna draw it again. All right, so it's kind of messy, but you can see here that there are some groups of boxes that are linked to each other and some that are not linked at all. Again, if we ran this a few times just with this random shuffle boxes, we would get a different looking graph. But we want to take each loop within here and color it. So I've written some code that I'm not going to go into much detail into, but it's actually coloring the loops to make them easier to see. We can use this, NetworkX has this nice function called simple cycles, which will find these loops. And then we're going to create a data frame that stores the loop number, just incrementing from the first loop to the next. And we will apply a color to each of these. So let's go ahead and run this code. And I'll show you now we have a visualization where each loop is given its own color. So it's a little bit easier to see. There's some different layouts we can choose that NetworkX has available to us that make it a little bit easier to see. So instead, so I find this layout is probably the easiest to visualize it because it tries to put them each in a circle, but you can see each box is now connected to each other because of the value within that loop. So I'm actually even gonna loop over this loop data frame, which we have now each node, we have assigned one of the loops incrementing from 0. So each of these will have their own loop number. That's how we got the color for it. We're gonna actually add that to our graph object. So we're gonna give it the loop number and give it a label, which is the node. And we're gonna create a function to create this graph object. And we're basically just gonna put everything together here. Now what we can do is we can take this create graph function that we've created before, and we can run it a bunch of different times and draw our results. And you can see that randomly, each time we run, there are different number of loops and there's different sizes of loops. And we can even find what the size of the largest loop is. And that's key, because if the largest loop is larger than 50, then the prisoners will not win or have very low odds of winning. If the number is less than 50, they are guaranteed to win. So this is just the results of the loops, and I'll do value counts on this. This shows us that for each of these loops, this is the size of the loops, and I'll take the max value and call this our max loop size. So we could see for this example we just ran above, the largest loop size is 31. So we actually know the prisoners in this box setup would be guaranteed to win with their strategy. Let's just take a second and also make this graph interactive. Now there's a library called PyViz that we can use for this. Essentially you can take in our network X graph and just make it into an interactive version. But the nice part about doing it this way is we can zoom in here and we can see, look, here's 12 is linked to 66, and that's the smallest loop here. So if I go into the boxes and I look up the position of 12, it's gonna link to 66. And if I go into the boxes at position 66, it links to 12. It's nice because this graph is interactive. You could zoom in and out. Just to finish this off here, we're actually gonna run this simulation and simulate how long the longest loop is every time we run. So we're gonna say the longest loops, we're gonna have to store them somewhere. And then for X in range, let's do T range, 5,000. We're gonna shuffle our boxes. We're gonna run it through this create graph function. And then like we did before, we're gonna calculate the longest loop. And then we'll just append that to the longest loop. So now we're running through the simulation 5,000 times, and we're storing how long the longest loop is each time. All right, our simulation is done running. If we look at longest loops here, gotta spell it right, longest loops, we can see it has 5,000 numbers and how long the longest loop is. The rest of this code is just to make the plotting so that we can color the results by if there was a success or not. And you'll see here, if I run this cell, that this is what the results look like. And this is really similar to the Veritasium plot that he shows in his video, where the odds of success here are all the times the loops are less than 50 on the left side. This is the 31% chance. And anytime the loop is larger than that, they're almost sure to fail this test. So while it's still important to have a good understanding of probability and statistics, simulating things like this sometimes can make it a lot easier to understand. And I hope this was helpful for you. Thanks again for watching. Thanks so much for watching this video. If you enjoyed it, please consider sharing it with a friend, giving a like and a subscribe, and letting me know in the comments what you enjoyed and what you'd like to see in future videos. See you next time.